Chapter 10, Section 4, Dividing Radical Expressions. This lesson will talk about dividing and simplifying and also rationalizing denominators or numerators with one term. First, let's go through dividing, and they're going to go through quotient rules, and which is the answer to a division, and really what they're doing again here is reviewing the properties of exponents that we've gone through before, or these rules where we can deal with division. Only going to show it in a radical form. The first rule here is a quotient rule for radicals. If I have, for any real numbers, the nth root of a and the nth root of b, and b cannot be equal to 0 because it's part of a division, and division by 0 is undefined. So there's a restriction on that. Well, we can take the nth root of the fraction a over b, and it's equal to the nth root of a over the nth root of b. And there's going to be some times when this is useful if we need to simplify something. So like in this example 1, they have the cube root of 27 over 125, and this b is the square root of 25 over y squared. So they go through these examples of how we could possibly use this rule. It's not really a new rule, but this rule to give us a strategy to simplify these fractions. So in this case here, the cube root in example A, the cube root of 27 over 125, we could split that into the cube root of 27 over the cube root of 125. Well, the cube root of 27 is 3, and the cube root of 125 is 5, so we just end up with this fraction 3/5. In this case, same scenario here with b is square root of 25 over square root of y squared. You get 5 over y, assuming that y is greater than 0. And they tell us any radical expression appearing in the answer should be simplified as much as possible. Or what we should, one of the things we've done all through algebra is all fractional answers need to be in simplest form. Well, example 2 here, they say it says simplify the square root of 16x cubed over 8y to the 8th power. And they show the work here. I won't talk through this whole thing, where they apply the rule, and then they're separating out perfect squares in this case. And I've talked about it last lesson and those kind of things. What I would really do is say this is 2 to the 4th power times x cubed, or x squared times x, and so on. And what they're doing is basically taking out perfect squares. And perfect squares are things with even exponents. So like y to the 8th power is the square root of that, or the half power of y to the 8th is y to the 4th, right? And like I said, we're going to talk more about fractional exponents. Well, they separate in this way to make sure that we can take out perfect squares in this case. In this one, they're talking about perfect cubes, so they're breaking this into factors so that there's a perfect cube, and then try to simplify that. The next one here, a couple more examples. If I have the square root of 80 over the square root of 5, they say that could be written as the other way. Going the other way on the rule here would be that when I have a square root over a square root, I could say that's the square root of that fraction, right? So this is the square root of 80 over 5. You can actually do that division or simplify that to be 16, and the square root of 16 is 4. Now how you apply that really matters. It's more of a strategy thing, but they're giving us a fraction bar separating the radicals. So we're going to do some things to work on that. Example B is shown here. Let's look at example C here, where we actually have 2 square roots of 2 as a denominator. In this one, we have the square root of 72xy over 2 square roots of 2. Now, this could be very easy to miss, but I can take this fractional part out and say it's going to be 1/2 times the square root of 72xy over 2. Because I can always put a 1 in front of anything when I'm factoring. So this is 1 times this, and this is 2 times that. I can say that's the same as 1/2 times a different fraction, right? So underneath here we still have 72xy over 2. Well, we can actually perform that division into 72, or simplify this fraction to be 36xy. And then 36 is a perfect square, so they could say it's 1/2 times 6, right, is the square root of 36 times the square root of xy. And then take half of 6, you get 3. So here is the most simplified answer right here. Now, sometimes we're going to run to, and usually it's a rule, just like always have simplest form for fractions. When we get into radicals, like I said, almost always, they get a little mark there that we'll look at the footnotes here in a little bit too. But it says rationalizing denominators or numerators with one term, and with a star. Well, the expression 1 over the square root of 2 and the square root of 2 over 2 are equivalent. But the second expression does not have a radical expression in the denominator. We can rationalize the denominator of a radical expression if we multiply by 1, that magic number 1, for multiplication, which is the identity. And the nice thing always about fractions is that we can find an infinity of ways to multiply by 1. We just need to find the strategy, or the strategy to get to the result that we're looking for. So what they've actually done here to convert this to this, they multiplied by the square root of 2 over the square root of 2. 1 times the square root of 2 is the square root of 2. The square root of 2 times square root of 2 is 2. And so on. And they'll show some examples with this stuff. And the way I describe it is a little bit differently than this one, which has the same effect. So if we have the square root of 7/3, the solution is to multiply by 1 under the radical, is what they do here. Why did they pick 3 over 3, which is a good part of this? They don't really explain that. Well, we want to get a perfect square in the denominator of this fraction. So how do you do that? Well, you square that. 3 is the easiest way, and you just say, well, then you take 3 times 3, or get 9. Well, I need to multiply by 1, so the numerator has to be 3 too. So I get 7 times 3 is 21, and 3 times 3 is 9. And why? Because we wanted the denominator to be a perfect square. So we can choose a strategy of what one we multiply by to create this scenario where the denominator of my fraction is a perfect square, because when I separate these out into a square root over a square root, I want this bottom, or the denominator, to be a perfect square, which I can pull out and say that that's 3 in this case. B is very similar, so in this case with cube roots. Example 5, they want to rationalize the denominator, and what that means is I do not want any kind of radical in the denominator of my fraction. So example A here, they got the square root of 4 over 5 times the square root of x. Now reality of this, when I look at this, there's really no way I can simplify this per se, because I'm not going to get other than the square root of 4 is 2. I could just say, well, it's 2 over 5 square roots of x. There's no factoring portions or even manipulation of fractions to get that to be in a different form, other than the issue that we need to rationalize this, which means I want to rationalize the denominator. Now, if you think about what does rational mean again, the set of rational numbers are any number I can write as a fraction using integers. Like integers are 0, 1, 2, 3, and so on. And they're negatives, -1, -2, and so on. So any fraction I can create from those integers is a rational number. So when they say rationalize, what does that mean? Well, we want to change this into something here that I cannot write as a fraction of integers. I can't write a rational number for what's in the denominator here or here. Okay? Like the cube root of 25. There's no rational number for that. Well, when they want the bottom or the denominator to be rational, so what we need to do is you multiply by 1 in a specific strategy to get rid of that radical in the denominator. So let's look at a here. So I have the square root of 4 over 5 square roots of x. Well, first thing they do is simplify what you can, which is square root of 4 is 2. I can't simplify this anymore. Well, the problem here is not the 5. 5 is a radical or rational number. It's this radical, the square root of x. So how do I get rid of that? Well, I can square it or take it times itself. And that's where they come up with this fractional 1 right here. This is actually equal to 1. But you got to think, why did they choose the square root of x? Because when I take square root of x times square root of x, this radical symbol is going to go away. And then we're going to get x. And then I need to remember how to multiply fractions. So I get 2 times the square root of x right here over 5 times x right here, because the square of the square root of x is x. So do I have a rational denominator? Yes. 5x, I can write that as an integer over an integer, or this x over 1 in a sense, because the x is prime. Kind of good to, pay attention to these words. Will help you remember when they start saying rationalize something. Means I need to get the radicals out of that denominator or numerator if they tell us to. Okay. This process here, a little bit more complicated example. And in this case, they say rationalize the numerator here in example 6. So what I need to do by what that's saying is I need this cube root in the numerator to go away. I want a rational expression up here. Okay. Well, the way to deal with this, now remember we're talking about cube roots, right? Well, 4 is 2 squared and a squared, so if I could get this to be 2 cubed and a cubed, I would have a perfect cube. Well, and that's where they get this 2 and this a factors to multiply by. And that's one of the reasons too I'd prefer to say looking for perfect cubes. I would think of this as 4 is 2 squared. Well, another times 2 will be 2 cubed, which happens to be 8. But in the same thing here, a squared, how do I get that to a cubed, is multiply by a. Okay. Well, I got to make sure I multiply by 1. So I've determined this is what I need to multiply the numerator by, the cube root of 2a. Well, I can only multiply by 1 and keep the same expression or equivalent expression. So I have to have the cube root of 2a on the bottom here too. So when we multiply this, I probably a lot of times would not show this step because I know what the result is going to be by determining what I'm multiplying by to be, it's going to be the cube root of 2 cubed a cubed, which is 2a. Okay, and then I have this cube root of 10ab on the bottom. So rationalize again means to make it a non-radical. And that takes us to the exercises for that, and 10.4 coming up next. Or this was 10.4, 10.5, excuse me.